So many of these speakers are people that I've just come to know over the years. Soroush is someone, we were talking about it, I think he's the speaker I've seen in the most different countries. We've gone to museums together, meals, all over the world. It's just been a lot of fun to show up and see him at a conference. Right now, he's an accessibility engineer at Square. You may have seen him when he was at NS Spain 10 years ago, so just take the X out of there, and that's when that was. He's here to talk to you about colors, theory, and practice. Please welcome Soroush.
All right. All right. Thank you so much, Daniel, for that warm introduction. Before we get started, I just want to give a big shout out to Luis and Borja and all of the organizers who put this conference together. It's really incredible to do a conference for 13 years. To be honest, I don't know of another one that's gone this long in the indie space. It's really incredible. So I just want to give them a big round of applause. Thank you all so much for putting this together, and it's my honor to close this out today. We're going to be talking about colors. When we're wrapped up here, I want you all to take away a couple things. Number one, I want you all to understand at a deep level what a color is. I want you all to understand how human beings perceive color. I want you to understand how we use technology to produce colors. And lastly, and maybe most importantly, I want to focus on what colors have to do with legibility. So to understand colors, we got to start way back at the beginning, and we're going to talk about the physics. So this is a photon. A photon is just a wave of light that's traveling through space. And the important quality of a photon is its wavelength. Basically, what's the distance between the waves? If the waves are very far apart, that's a radio wave or a microwave. If the waves are very close together, that's a cosmic ray or an X-ray. What we're interested, though, is this little area in the middle that we call the visible light spectrum. But why is it that we can see this particular band of photons, but we can't see the one next to it on either side? And the answer is evolutionary, believe it or not. When our ancestors were in the ocean, it turns out to be very useful to perceive these waves of light, but water absorbs most of the electromagnetic radiation. There's a narrow band in which it allows that light to go through and penetrate, and when our grandparents were fish, this is what they used to see. So we've got our photon, our humble photon, and wavelength is really important, not just for what kind of wave it is, but also what color that wave appears to us. So again, if those waves are really close together, that's going to be more like purple and blue. If those waves are farther apart, it's going to be more like red or orange. When those waves hit our eyes, we need to convert that into some kind of electrical signal that our brain can understand. So that's where the biology comes in. We have two types of cells in our eyes. We have rod cells and we have cone cells. Rod cells, we have tons and tons of them, 10 times more than the cone cells combined. And they cover the back of your eye. We're not going to focus too much on rod cells. They are responsible for perceiving amounts of light and relative brightness, but they don't do much for color. We're going to focus more on the cone cells, which are kind of focused on the center of the back of the eye. So you have short wavelength cones, and we commonly call these blue. They respond sort of in this 420, 430 nanometer range. You have green cones, which are also called medium wavelength cones, and those respond a little bit higher up in the spectrum. And then lastly, you have your long cones, and those respond a little bit higher than the green. Now, these three types of cones together, they make up what we call your fovea, which is the part of your eye in the back, in the center, that is responsible for determining colors, basically. And now that we understand the different types of cones, we can start to understand the different types of color blindness. If you're missing your red cells, you have what's called protanopia. If you're missing your green cells, you have what's called deuteranopia. And these two actually are both called red-green color blindness. If you're missing your blue cells, you're going to have tritanopia. And the reason that both protanopia and deuteranopia are generally referred to as red-green color blindness is because these curves are so close together. They can kind of compensate for each other if you're missing one or the other. They kind of react to some of the same photons. So for example, if we have a photon that comes in at, let's say, 510 nanometers, you can't trigger the green one without also triggering the red one. You can't trigger the green one by itself. And this turns out to be very important for how we perceive color. What I said just then is not exactly true, but I will get to that in a moment. This is the human gamut. A gamut is basically a fancy word that means a full spectrum of color that can be perceived by something or produced by something. And you see, in the human gamut, if you look at it in this perspective, there's just nothing up here. We can't perceive these colors. And the reason that we can't perceive these colors is because if you try to send a photon that just triggers the medium cones, you're also going to trigger the long cones, and you're going to get pushed down. So there's all these colors up here that we can't perceive. But there are some scientists that actually figured out how to make it happen. This is a paper that was released earlier this year. And the technique that these scientists have is that they find your medium cone cells in your eye, and they shoot lasers directly at those cells, which is crazy, right? Unbelievable. They call this color OLO, and the participants in the experiment, they report seeing a color that is a very vivid cyan turquoise color, and this is where it would be if other humans could see it. So probably only 10 people in the world have ever seen this color. And again, it's because of where those cones are. So that's what would happen if you could trigger just the one cone without triggering the other cones. Now, we have these three types of cones in our eyes, and so when we produce colors, we want to be able to trigger these three types of cones independently to be able to make different colors. And so that's when we get to the technology of color. So this is a humble pixel. It's got a red subpixel, a green subpixel, and a blue subpixel. And this is one subpixel layout, putting them next to each other like this. There are others. This is probably the most common. But it's gonna be enough for us to understand colors today. But before we talk more about pixels, I want to talk about color spaces. So imagine you have a black point floating in the middle of space. It's really black. You almost can't see it. And you put a red point next to it, and you can draw a line between those two. And these are all of the colors that have varying amounts of red in them. Red is only one axis of our color space. We also have a green axis. And so if we go up from the black point up into green, we get to this really hypersaturated green color. But what happens if we start at the red point and go up into the green dimension? And it's a little bit counterintuitive, but the color that we get to is actually yellow. So if you're used to mixing paints, this is not something that you would expect. You would expect more of a brown color. But light doesn't behave the same way that paint does. It mixes in a different way. So we're going to flesh out this kind of color space a little bit. And we're going to add our last axis. And so because this is a space, it's in 3 dimensions. And so we can kind of look at it from that perspective. And we need to look at the secondary color where green and blue meet, and that's going to be cyan. All right, flesh that out a little bit. Pretty good. And then there's one more secondary color, which is going to be when red and blue meet. That's going to be magenta. All right, so we got our color space there. And then when you mix all 3 colors at full capacity, you get to your white point. So we can put in all the little edges of our color cube, and we can also fill in all the walls. And here we have our color space. I really like actually just kind of panning around this, just because some of the colors are so interesting. Like this really nice coral right here, and like any point inside this cube is basically going to be a valid color for us. I just think it looks really great. Cool. So back to our. Thank you. Reality Composer Pro, pretty good. So yeah, back to our pixel. We got our pixel here. And as we dial down and up the amount of red and green and blue in our colors, we're going to get to different colors. So I've taken that pixel and I've scaled it down. I put 30 next to each other. Now, if you zoom right in, I can see from here, there's no other colors here other than red, green, and blue. But as we dial up and down the amount of a certain color, you're going to perceive something else. Especially if you're in the back or if you squint, you'll see it better. So this is SwiftUI's red. And it's 100% red, 27% green, 23% blue. And if you look at the pixel grid, it looks pretty red. If we crank up the green, this is SwiftUI's yellow. And when I'm looking up really close, I see red and green bars. But the further back you get, the more this is going to look like yellow to you. Same with cyan. If we crank up the blue and the green and we dial back the red, we're going to get this cyan color. Again, I'm not actually showing you a cyan color in the middle. You're perceiving a cyan color because the colors are so close together. I hope it looks like that to y'all. If it doesn't, just squint and pretend and tell me that didn't work later. So, color spaces are really important. They're not just important for picking colors, but they're also important for kind of moving through space and understanding what a path in a color space looks like. So here we have one path through this color space. So that's white to black. That just creates that creates our gray gradient. And this is a perfectly fine gradient. But if we look at another gradient and go from blue to yellow, we actually note that we go through the exact same point in the middle of the cube that is on our white to black gradient, which is really strange. So put another way, when we go from yellow to blue in an RGB color space, we end up at this point 7F, 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 right in the middle that's just gray. And we started with these two really vivid colors on the sides, and we ended up at gray. And it's very strange that that happened. The way to fix this problem is to change our perspective. If we look at our color space from the top, and we look at it from the white, and we consider that to be the top, and we look down, we see that the hues kind of create a circle. And as you go around the hue, you add and remove different amounts of blue. And so if we could change what we were seeing and the way we see it, we can create a different color space. So this is what's known as the HSL color space. So white to black in the middle, that's going to be lightness. And then this axis here, going out to the different colors, is going to be your saturation axis, how saturated a color is. And then the last axis is rotational. It's a polar coordinate system, so you can go around by a number of degrees. And that's your hue. So your hue is represented by an angle in this color space. And that's really beneficial because it means you can go from green to yellow without changing your lightness or your saturation. And another way to look at this is this little model. Again, thank you, Reality Composer Pro. This is white at the top. This is black at the bottom. And all of our colors kind of go around the side. Every point inside this bicone is a valid color in HSL. And so if we kind of take a slice out of the middle of this cone, we would get to what we would call the hue circle. And the hue circle basically allows us, instead of going from yellow to blue directly through the middle, we can go from yellow to blue around the outside. And this enables us to build a gradient that stays really vivid and colorful throughout. So the color space is super important for determining what your motion is going to look like. The coordinate space tells you what your motion looks like. So this color space also actually has its problems. But to fix those problems, we need to talk about human perception, and we're going to talk about perceptual color spaces. So there's this guy, his name is Albert Munsell. As far as I can tell, he's the first person that really figured out this perceptual color space stuff. He was trying to make what he called a balanced color sphere, and he wanted to make something symmetrical. But every time he brought in people to study and he asked them about different colors, he would find asymmetrical results. So he would look at these colors and say, why do people see more different types of red than they do for this teal color, for example? So here in our gradient, we have all these colors, and I'm actually going to pipe these colors through a little algorithm. That algorithm is called the luminance calculation. And there's not too much to know about this, but a couple of things that are important. Basically, we're saying that this is how humans see a color, how bright humans see a color. So 21% of that brightness comes from red, 71% comes from green, and only 7% comes from blue. So if you add all of these up, it is 1. So if you pass the color white in, you'll get a luminance of 1. If you pass the color black in, you'll get a luminance of 0. If we take our gradient and we push it through that luminance algorithm, we get these colors. Now, immediately you notice that blue is way darker than you thought it was. But also, right in the middle, we actually go up in luminance, going to cyan, before we come back down to blue. So when we move through this color space, we're not actually linearly moving in terms of the human perception of color. So HSL is a really good color space in some ways, but it doesn't deal with how humans see color. We can take the whole hue circle and push it through the luminance algorithm, and we can see that blue, again, very dark, yellow and cyan are pretty bright. There's even a little bright spot near magenta. But these colors are not really the same. Even though they're kind of pure from an RGB perspective, they're not perceived the same by human beings. So Albert Munsell, when he finished his work, he produced something that he calls the Munsell model. and it looks like this. And again, you can see it's just totally asymmetrical. It's just the way that we see color is so different from some of the models that we have in our computer systems. Color just does not behave the way you think it does. It does not behave symmetrically. It does not behave sort of evenly. Now, there's lots of different perceptual color spaces. There's CIE Lab and CIE Love. They're very old. OK Lab and OK Love are newer versions of those. But the one I really like is LCH, Luminance Chroma Hue. Now, this is not an exhaustive list of perceptual color spaces. There's even more. But these are some of the highlights. I like LCH because it maintains the hue angle property that I really like. And so hue is a number of degrees between 0 and 360. Luminance goes from 0 to 1. That's just basically white to black. And chroma represents how saturated a color is, how much of that color is there. Chroma, you'll notice, only goes up to 131, which is a very weird place to draw the line. And that brings us to one of the very special things about this color space, which is that the chroma is actually unbounded. So you can put in a value of 135 or a value of 140, and that color may not be representable on a screen or on a projector or on your phone, but it's still a valid color. And you can even take it higher, and you can make colors that are not perceivable by humans, but they're still valid colors in this color space, which I think is so cool. If we make a hue circle out of LCH and we pipe it through the luminance algorithm, we see it's totally flat. Every color has the same luminance, which is very, very awesome. These are what the LCH colors look like, and I think they're really cool. SwiftUI also has a bunch of tools for working with perceptual color spaces. There's this API for mixing two colors. Here we're mixing yellow and blue by 20%. And you can pass in a third parameter, and that's in color space. So the default color space is device, and this is going to give us kind of the RGB that we were looking at before, where you go through this gray value. You could also pass in a perceptual parameter, and this gives you a totally different gradient than the ones we've seen before. So when we push that through the luminance calculation, we see that the amount of luminance steadily decreases in this color space, which I think is very, very cool. I have it on good authority that under the hood, this is using OK Lab. Unfortunately, it's Apple, so they did not publish this as official documentation. But I'm pretty sure it is OK Lab under the hood. So putting our three gradients next to each other, we have the RGB at the top, we have the HSL, and we have the perceptual one from SwiftUI. Any color space you choose is going to have a slightly different gradient as you move through that space. When you work with SwiftUI, you can mix colors, yes, but you can also make gradients, and those gradients can have a color space sort of modifier on them. So there's a device version and a perceptual version. These are also useful if you're working with gradients, mesh gradients, anything like that. Try them both and see which one looks better. Probably perceptual will look better, but your mileage may vary on that. And that kind of brings us to the last section of the talk, which is how we read. For a bit of text to be readable, it needs to maintain some level of contrast between the foreground and the background. So this is the audience participation part of the talk. Can you raise your hand if you think example 1 is easier to read than example 2? Nobody. OK. What about example 2 over example 1? Anybody think that's easier to read? OK, we got some hands, so pretty much everyone agrees. Yeah, I agree too. Example 2 is much easier to read, but it's not enough for us to just agree in this room. We have to kind of agree as a society. So we need some way to be able to tell other people that we think these two colors are readable. We've created an algorithm. We call it WCAG2. We've been using it for about 20 years. And this is what the algorithm looks like. No need to worry about it too much, but it's a gamma correction, and then those three same coefficients for luminance, 21%, 71%, 7%. And then calculating the difference between the brighter color and the darker color. That's basically it. I'll have a gist with all this stuff at the end, so you can, with a QR code. When we take our two pairs of colors and we ask WCAG2 about them, we get these numbers, 1.5 to 1 and 6.7 to 1. You get the sense that maybe bigger is better. But we need some kind of scale to judge these things on. So WCAG2 comes with a scale. Anything above 7 to 1 contrast ratio is a AAA rating. Anything above 4.5 is a AA rating, and everything else fails. So our pairs here, the second example passes, the first example does not pass. I'll show you another example as well. We talked about how blue is actually a very dark color and yellow is actually a very bright color. Here's some proof of that. Does anyone want to vote for example 1? Okay, nobody? Everybody's good with example 2? Yeah, WCAG2 agrees with that. 2.4 to 1 for the blue example, and a staggering 19.6 to 1 AAA rating for the yellow example. Much, much easier to read. WCAG2 is a really amazing algorithm, but it actually also has some flaws. There are a couple of places where it's not performing as well as we want it to perform. And so I want to share a couple of those examples. There's going to be more audience participation here. Who wants to vote for example 1 here as easier to read, higher contrast? OK, I see a good number of hands. Who wants to vote for example 2 as easier to read? OK, I see a few hands there too. All right. I would say generally there were more hands for the white text over the black text. But WCAG2 does not agree with the consensus of this room. They actually give the black text a AAA rating, and they fail the white text. So that's a little bit interesting. I think this one's cool, too. Who thinks example 1 is easier to read, has higher contrast? OK, a couple of hands. Who thinks example 2 is easier to read? OK, I definitely see more hands there. I agree with the example 2 people. WCAG2 does not agree. They think these are the same. So that's a little strange. Couple more examples. These are the same colors, but just flipped, right? So blue on white or white on blue. So who wants to vote for 1 here? Who thinks 1 is easier to read? OK, I see a few hands. Who wants to vote for 2? OK, I see more hands there. I agree with y'all, but WCAG2 does not care. WCAG2 does not care about which color is the foreground or which is the background. It just cares which is brighter and which is darker. More examples. Bold text. Who thinks the unbold text is easier to read? Couple hands. OK, maybe 10, 20. Who thinks the bold text is easier to read? More hands, maybe like 60. WCAG2 does not care about boldness. These are the same to WCAG2. Another example, font size. Who thinks the smaller one is easier to read? OK, good. No trolls in the audience. Who thinks the bigger one's easier to read? Yeah, there we go. So the solution to these problems is a new algorithm. It's called the Accessible Perceptual Contrast Algorithm, APCA. And it takes into account a couple of things. First, let's look at the algorithm. You'll see again, you don't need to worry too much about the details here. Again, there's a gist at the end. But that luminance calculation is here again, 21% red, 71% green, 7% blue. So those numbers are still there. APCA takes into account, of course, the colors. It does a better job with perception than WCAG2 does. It takes into account the polarity of the colors, which one is front and which one is back. It takes into account the font size and the font weight. So back to our examples. Here, where the majority of the room said the white one was easier to read, but not everybody agreed, APCA agrees with the majority of the room here. They say that that is a score of 61, which is better than 48. For this example that WCAG scored equally for both, APCA scores the one that agreed with the rest of the room, that most of the room, at 77 over 46. For these two colors, they're actually very close, and that was reflected in our poll. They're only 65 and 71, so they're very close together, but APCA does consider 2 to be more readable than 1, which I think was also the general consensus in the room. For font weight, APCA actually scores these the exact same. But APCA also comes with a set of lookup tables. So depending on how big your text is and what weight it's at, let's say our text is size 18 and it's regular text, you need a minimum of 75 to be considered readable. Our text is 62, so it's not considered readable. If we go back to the lookup table and we crank it up to bold font weight, then we see we only need a score of 55 to pass, and we have 62, so we're good. Same here. APCA does not, the algorithm itself, the number you get does not get affected by the font size or font weight. But again, in the lookup tables, if we take our size 18 font and we crank it up to size 28, we see that we need a minimum of a score of 55, and we have 62, so we are considered passing. That is APCA. It does have a few caveats. This is an algorithm that's still being tested, so it's not finished yet. The constants might change, the lookup tables might change, the algorithm might change before this algorithm is considered to be finalized. If you have any government regulations that you need to conform to, like the European Accessibility Act or the American Disabilities Act, then you should keep using WCAG2. But there's nothing that stops you from picking colors that pass in both. So you can find a color that passes WCAG2 and a color that passes in APCA. And then when and if APCA becomes a part of WCAG 3 and is totally finalized and ratified, you will already be ahead of the curve. So if you want to use this stuff, a couple resources. OKLCH is a really great color picker. CSS.land/LCH is another very good color picker. And these let you work with these more interesting color spaces. I wrote the algorithms for APCA and WCAG 2 in Swift. I put up a gist. And I also included some code that you can give it a foreground color, a background color, and let's say a font weight, and it will tell you the minimum font size that you need to be considered readable. Those resources you can find at this QR code. And I just want to say thank you to everyone for coming to NS Spain 2025. Oh, man. Thank you.
So, how many of you saw colors as the title went, that was so awesome. Number one question wasn't a question. Very interesting. My head exploded.
Cool.
So, we're wrapping up for the day, but before we do, instead of asking you about colors, when you were looking at color spaces and taking the cube and spinning it around, that wasn't Keynote, was it?
Huh. You noticed that, did you?
Tell me a little bit about that.
Okay, so I have to apologize here. I took a note out of Chris Eidoff's book, and this is actually a totally custom app. Let's see, where's my mouse? So this is a totally custom app that basically serves to be the presentation. Everything you saw was basically Swift UI. This is Swift charts. These are, yeah, pretty good. Whoop. Come on, scroll. Let's go. Doesn't want to scroll. I don't know what's up with that. Yeah, these are shaders, actually. These are shaders, and so that's how these are drawn. So these calculations happening live for you. So you know that these numbers are accurate. All of the APCA calculations were done live. There's no trickery. I didn't type in the numbers. They're done using the very algorithms that I put on the GitHub. This is the Xcode project for it. So you can just see here. Let's jump to the top. Oh, yeah, this is right. So yeah, this is the talk. This is the whole talk. So yeah.
Yeah, Soroush said, I wrote my own app, and I said, yeah, of course you did. Please again, thanks, Soroush.
That was so good. Thank you so much.